So it's my really great pleasure to introduce Professor Ballal. In fact, I would start with the one line while I was doing MTech at IIT Bombay. He was very popular among students and I got the chance to attend few of his lectures. He's a wonderful teacher, I can say you that. So just a brief introduction about Professor Ballal. So Professor Ballal is a distinguished Indian academician and a researcher in the field of metallurgy engineering. He joined IIT Bombay as a faculty member in 1979 and retired as a professor emeritus in 2020. He received his bachelor's degree from NIT Surathkal in 1971. He then obtained his Master of Technology degree in Metallurgical Engineering from IIT Kanpur. He subsequently joined for PhD and completed his PhD from IIT Kanpur in 1979. Professor Ballal's research interest includes process metallurgy with special emphasis on iron and steel making, thermodynamics, heat and mass transfer, mathematical modeling of processes, practices of traditional metal artisans of India. So with this, I welcome Professor Ballal and please continue. Yeah.
Thank you. Hello, hello. Is it on? Seems to be on. Hello. Hello, you can hear? Yep. Okay. Good evening. Late in the day. And after this inspiring speech of Professor Manna, difficult to pick up the tempo. Okay, so we will just, I'm talking about iron heritage of India. Actually, I'm not going to talk of iron heritage of India, I'm sorry. I'm going to talk about the people practice of the current generation, a little earlier. Now I have not been in touch for 25, 30 years. Let's go hard. We all know that India has had a very, very glorious heritage. If you see, this is somewhere close here, 70, 80 kilometers, Dhar. It's a pillar which is it is in three pieces. It has fallen down. I don't know what is the history, probably about 10th, 11th century, Raja Bhoj or something. 14th century? 11th century, yeah. Yeah, 11th century, yeah, that's what I thought. It's broken into pieces and, some people have taken the trouble of putting them. It was apparently scattered around. One piece is still missing. So, and so on. So there is this pillar on top of the Western Ghats in a place called Katachadri. This is supposed to be the place where Adi Shankara is supposed to spend some time on his way north when he was very young. That's a pillar. We don't know the history of this, except that somebody tried to dig it and couldn't do it. And so,
2nd century AD. Is it
this one?
Already? It's dated. Some people are done to it.
Dated, okay. Is it IIT Bangalore? Professor Ranganathan School?
Also has a paper on this.
Yeah, they've all written papers. So, the thing is that this is where 3,000 millimeters, 3,500 millimeters of rain every year. It is on top of the Sahyadris. You can actually from this point see the Arabian Sea, though it's about 50 kilometers away. So it's a very high point, very near to Kudremukh. This is the Konarak everybody knows, and you can see that these were the supporting beams. And India large spans can only be covered with the beams. Stone beams are not very distinct, and they had perfected this, and so on. Now of course, many of them are fallen down. The Puri temples also has similar kind of structure. This is one of the large beams, large guns of the Bahmani period. This is probably the longest, gun cannon of this type in northern Karnataka, southern Maharashtra, somewhere. This, of course, everybody knows, and pillar. So We have this hoary tradition of iron. So if you're looking at the iron heritage as such, I am more concerned about making of the iron rather than its properties and so on. So the early references in the Veda, everything in this country has to go back to Veda, unfortunately. In the Veda, the references to iron exist, but of course the Rigveda references are contested as to that there's reference to Ayas, contested. Atharva Veda also, by that time probably it is referring to iron. Of course, Atharva Veda time I don't know. People may say 500 BC or even earlier. Again, these days it's extremely contentious to talk about times. Atharva Veda, there is reference to, for example, Ayo Damstra, iron tusks. That of course refers to saying that let you have, Jata Veda, that you have the iron tusks so that you can kill. This is all in Shatru Nivaran mantra kind of thing. And then Ayo Mukha, that you have a mouth full of iron kind of teeth and so on, and Ayo Jala, all these. But references to the making of iron is missing. Of course, Atharva Veda contains something else, but making of iron is missing in all these texts, which is interesting. Atharva Veda contains heat treatment procedures, which is extremely interesting. For example, for different applications, what different liquids we use. You can use hot water, you can use oils of different kinds, you can use milk, you can use, for example, fish bile, depending on what is. You want to make a chisel for the stone, you want to do a sword, those kinds of things. And also using, we had this interesting practice of heat treating using, for example, pumpkin. If you want a knife and you want to do one stage quench and temper, you do it with this kind of very highly fibrous but full of water kind of thing. And if you want to do a sword, you do it in a plantain. If you plunge a hot thing onto a plantain tree, for example, I don't know, if you have cut a plantain tree, you would know it's full of water, but it's highly porous, highly fibrous. So what happens, as soon as you punch, of course, the water will quench, but it will also evaporate and go away. What is left behind is the insulating layer. So it will insulate, so it will recallus. From the inside, the heat will come out, the outside surface which has got quenched, now will get tempered. So, and of course, this is not left to India, but India, we used to use these humane methods. I won't name the country. There are swords made and then heat treated by, apparently, anecdotally, plunged into some big bellied fellow's belly. Yeah. So those kinds of things. Some references are there. Anecdotal references are there on the quality of Indian iron. Of course, there are, by the turn of the present era, of course, there are many references to the quality of Indian iron, but even in 5th century BCE, some ambassador's Greek fellow is offered a sword, and Alexander, there is this porous giving him some 20 talents of iron. I don't know whether it's ingot iron, for him to make I don't know what. The iron trade is very important in the Durga Nivasa. He's talking about where should the ironsmith be. Ironsmith is just next to the palace. Iron industry and the gold industry are next to the palace because it's very important. And of course, there are customs duties on iron, this thing, etc. But again, the details of the iron makers and the making procedures are missing in most of these Sanskrit texts, which is interesting actually. That is missing. Many of the other things are given in these texts, but iron making is missing. Of course, archaeological evidences, there are archaeologists around, so archaeological evidences, we go back to now, I think people do accept about 1800 BC, approximately, 16 to 1800 BC. There are iron objects which is already there in Hallur, which is about Hallur in Karnataka, which is about 1500 BC, 1300 BC, dated, and of course the recent, I'll come to that. Of course, otherwise our iron making knowledge is from travelers, and unfortunately very recent ones, and most of them are European travelers who have talked about iron making. I hope I'm not making, there are too many experts, I'm a little nervous, of all kinds. Everybody knows if I talk about Sanskrit, there's somebody there, somebody from archaeology here. Okay, so anyway, so this is now everybody quotes for iron dating, which is from Tiwari's work, somewhere around 2000. This is in UP, UP otherwise, in the plains of Ganga, there are no iron objects. But you see, just below Benares, the Vindhyas come almost up to this point. And this is the region. It is still probably hilly, because there are technological reasons why in a very, very wet kind of a land, iron will not be practiced. Okay, anyway, so this is 1800 BC calibrated, somewhere around that. So now, and this, if you see a furnace, this is the furnace we saw in 1995 or 93, exactly like this. And I saw a furnace of this type, just the base like this, just outside Hampi, which is Vijayanagara's Hampi, just outside the Hampi University, Kannada University. There is a farm, and there is one corner, there is this thing, farm was full of iron slag, and so on. So in the sense, by this time, therefore, 1800, this is a fairly well-established technique. It's no longer a hit and miss kind of a, looks like. So why study this? So there is this historical importance, that's what we are talking today. And what interested us more was that there were existing practitioners. We were more interested not in the past, but about who are we? The question as to who as Indians we are. So most of the time it's about Bombay, Delhi, and so on, but these are also our people. And these are the Agariyas, they're still practicing it. So what is their strength? What is their strength? So that was very, very important, because we were also part of, this is the alternative, looking at alternative to the modern knowledge paradigm was also prevalent during this period, 70s and the 80s. And for me personally, what was interesting was that, see, these technologies have been built with an alternate epistemology. In the sense, it is not based on scientific principles that we understand as we borrowed from this thing. They have their principles on which, for example, if you talk to an Ayurveda doctor and tell him, no, why don't you do some blind experiments, etc., he says, no, that is not our method. You are assuming that we didn't have a method to verify. We have our own epistemological base. And similarly, these have come through some other knowledge paradigm. So that is interesting, this knowledge between what we are trained in. That's why we got into this as such. Okay. So now the study that we did is in this region. This is basically a documentation. We also did some 2-3 years of experimentation at IIT Bombay. So you are somewhere here. This is Nagpur. This is Hoshangabad. So you can locate Indore somewhere here. So this is a place called Balaghat in MP. This is in Sarguja district. This is actually Jashpur Nagar. I'll show you another map. And this is Jashpur. This is below Mirzapur, in a place called I'll come to that. And this is near, in a place called Bishunpur on the way to Netaraja from Gumbla. So it's in Jharkhand. Yeah, here is the one. So this is the Wadraf Nagar. This is Balaghat. You can place this Nagpur, and so on. So that is Ranchi. So these are the places where we did documentation. I spent some time, but my students, a couple of my students spent a month or so observing, and so I'll just go through, this technology that they were using. So let's go through the equipment first. It has basically furnace, bellows, and the tower. This is just a schematic. This comes from census, this thing, just to illustrate. So the furnace is typically of this size that we saw, though in the record, for example, in the 18th century, some Royal School, Royal Society record, there is a Hoshangabad furnace, which is much larger, okay, which is recorded in Dharampal's book on the 18th century science and technology. So this is about less than a meter, right? And just made of clay. You have a blowpipe here, and you blow through bellows. And that's it. You charge charcoal and ore, keep the furnace in operation for about 3, 4, 5 hours. We'll see a little more detail. This is just a schematic. You see these bellows are operated with this bamboo, which act like springs. Okay, so this is that Bishunpur. This was the reconstructed furnace, in the sense that the furnace was not existing, but this old man called Nagu Birjia Asur, he's a Asur. Okay, please note this. Some of these people are called Asurs. Yeah, let me go back to this graph. So this band that you're seeing here, the Verrier Alvin, who did a lot of work among these people, calls the Agarias, all of them, though they call themselves by different names. Some of them call themselves Agarias, some of them are Asurs, and then different Lohras and so on. We looked at the Birjia Asur. So that man who comes from Nagu, he was of uncertain age. Only thing is his great grandson was working with him. His photograph may be there somewhere. Yeah. So that is one kind of furnace. I'm just showing one of these furnaces, slightly inclined to the front. It's about 0.85 meters high. This is another furnace. This is upright. This is in a place called Sela, very near Ghatgaon, Jashpur Nagar. These are Lohras. They call themselves Lohras. And they interestingly use magnetite sand as one of their ores from the river, because magnetite sand gets blown off, and that is naturally concentrated. So and very difficult to smelt. So these are tall furnaces. This is the furnace from Wadraf Nagar, that is below, in Sarguja district, below Mirzapur, just as you enter MP. And this is the smallest furnace that we saw. But their ore is also very lean there. The ore is full of gang. So this is the only, in the earlier two furnaces that I showed, there is only one opening from which both bloom after it is done is taken out, as well as slagging is done. Whereas here they have a lot more slag, so they have a separate slag hole. This is from Balaghat. This is more like the schematic I showed here. Different furnaces, different types. Though they are all of this about a meter high. So this is entirely different. Of course, this is near that Sela. These are also Lohras. This is in Ghatgaon. They're probably related. That only 7 kilometers apart, 7 or 8 kilometers apart. They're probably related. This is a furnace not as constructed. It is excavated underground. So the mud itself, just bored a hole, and that's another this thing. Again, this is a tall furnace. Yeah. So yeah. So this shows one of the furnaces, the tall upright furnace. That's about total about 1050 mm. Part of it is underground. Part of it is all in all these furnaces. This is the shortest furnace, about 720, and so on. Yeah, these figures have been drawn by my students here. This we have actually measured very carefully. These are of course quickly measured. Just to get you a sense that that's a typical 10,000 tons per day blast furnace, and this is the Agaria furnace. Just for size comparison. So, and then the bellows. These are interesting bellows. These are foot bellows, operated with foot. So and it's a wooden box covered with a skin, with a small hole here, and a thong holds it like this, and that is the bamboo. It may be coming this way or that way. Now what you do is that, and this is the blow pipe, which will blow to the tuyeres. Now, what you do is you stand here. Okay, so that gives you a picture. They're always in twos. They're in pairs. So you stand with your heel on the hole. So you close. So it's a one-way wall. So you close and press, and then when you leave it, automatically it opens. So you go that way. Go that way, and you just imagine it's about, depending on the type of ore, it's about 5 to 6 hours of work, and you go through the process. Let's say we saw this at Gangaur for about 5 hours. About 4 hours you go at about 100 strokes a minute. 100 strokes. Towards the end, when you're about to finish the operation, you ramp it up and go to 120 to 130. You just imagine standing on it. I did not last for 5 minutes on it, like that. But of course, it's a husband and wife operation. Please, it's not a men's. The interesting thing is this technology is by husband and wife, and the technology holder was the wife. Please note. Yeah, the technology holder was the wife because some of the finer techniques are done by the wife. Okay, the hard work is done by the man. Okay, so this is what the tuyer is, and the tuyer technique is that's a tuyer. At the end, it should have molten like this, neither more nor less. If it doesn't melt like this, the iron is not made. So, and this tuyer therefore is constructed by the lady of the house. This is our reconstruction at IIT Bombay. We built different types, for about 3 of them. 3 versions were there. So anyway, raw materials I have already said: iron ore lumps, magnetic sand, charcoal from hardwoods, and atmospheric air. Of course, the magnetic sand, they would do concentration, just like we do by gravity. He'll put it on the slope, put the sand, put water, so that the sand which is lighter flows out, and the dark one stays back, and that he loads. The charcoal, of course, is made. I don't know whether students know. Most of the students have left. Yeah. But what they insist is that for smelting, they need hardwood charcoal. So this whole business is in the Sal belt. India has a Sal belt starting from somewhere near Patna or so, and comes all the way down to Andhra Pradesh. Sal. Sal is a hardwood. It's almost as hard as teak. Because they would like to have teak, but teak is too expensive. Whereas for the smithy, they will take anything. Some softwood is okay. They need hardwood. It is something to do with the ash. I think I'm not too sure. We did some half-hearted attempts to understand this, but they say that if you don't use hardwood, so when we got the Agarias to Bombay, and they rejected most of the charcoals that we could procure locally. And finally, we had to go to a sonar, and sonar had some good, some kind of a black looking stuff, and they said, okay, ye isko chala denge, kind of thing. So that is a secret that we couldn't understand why. So this is the demonstration. So this is the furnace in operation. You can see the flame shooting out. But this is not what is interesting. This was done for demonstration for a conference in IIT Bombay. But this is the actual operation. Somebody who is making iron and making tools and selling it to people. So and you note that this is done in the night. In the night. This is around 1 o'clock in the morning. Okay. And that's how it is always done. And halfway through he'll start doing slag off. The slag has to flow, and this is the quality control. If they see the slag of the right type, not too much, but lack of slag means iron is not going to be produced. So slag has to flow out to some extent. The tour is like this, please. This is, of course, a photograph from IIT Bombay. Tour is like this. It's of the inspiration type. Then the blowpipes from the bellows don't come and join, seal. They are just kept in front. So it is like the inspiration tour. So when the jet of air goes, it also brings in atmospheric air. So if you blow 100 liters per minute or so, you'll probably take in another 50 to 75 liters of air from outside. That's how. So because it's open type, we could use, of course, in IIT Bombay for 3 years. I'm not going to get somebody who'll sit on a bellow and do this 6 hours of operation. I have to get the whole hostel as volunteers and pay them some, tea, coffee, samosa. So we made a contraption using this thing, but then simulating the bellow operation of periodic operation by using some relays and so on. So at the end of this operation for around 5 hours, you break this wall. That opening is close to temporary wall. It's broken here, for example, and then he will take out the bloom, and then bloom has to be immediately forced, because the good bloom in this operation is that when it's taken out, iron is solid, so you have the bloom, but the gangue is liquid. So that as soon as you take it out, because the iron otherwise are all granules coming from the, it's like the DRI. So as soon as it comes out, you have to squeeze out the slag. So that's why the temperature is very crucial. If it's too low, then the slag is also not molten, so you can't squeeze it out. Then you just put one hammer on top, it will break into pieces, which used to happen most often to us in IIT Bombay. Or iron will melt, and if the iron melts, it is catastrophic. They don't want the iron to melt, and you know why? Because as soon as the iron melts, it will pick up all the other things. It will pick up silicon, manganese, it will pick up everything else. So you don't get that quality of iron if it melts. So the Chinese always melted, but then they cast it. It is not forged material.
But your temperature is not very high here to melt the iron.
No, yeah. No, you can go. No.
Depends on the blowing and the amount of air which you have put.
It depends on the size of the furnace. You go because you go higher. You form the iron, and then you spend enough time inside in charcoal. You pick up carbon, and the melting point falls. So Chinese furnaces are longer, heighter.
Cast iron melting.
So because Chinese were always very, very good in casting. So they always cast it, and then of course they would decarburize for whatever steel, like they used to do in blister copper and so on. So whereas here actually we saw one place where apparently there was a place, it was all overgrown with several furnaces and very interesting furnaces, but they won't let us get in there. They think no, that is a haunted place. I asked, of course, they won't tell us, they won't allow us. From a distance we saw. They won't allow us to say. And then I asked that fellow who was accompanying us, because who was giving us some. He said, "Sir, वहाँ pickle गया. एक बार pickle गया तो they think it is haunted. You know, their furnace, their gods are unhappy with them. Yeah, because their gods are unhappy. That's why it has happened that way. Yeah." This is the Smiti operation. This is in Ghatgaon again. You know, that is their bhatti. But right now he is doing some Smiti operation. They're using, you know, this is where it is. This fellow is a young man who was also working the dugout furnace. He was working it. Now, that is about the technology. I've gone through it briefly. If you have any questions, you can ask later. So, there the interesting thing we found in this Bishunpur, in Ghatgaon, we talked to a farmer who was there. Very interesting, actually. We went there looking for leaving practice. We had already seen in Bishunpur, but then it was reconstructed out of memory by this old man. He had seen it when he was very young. After that, the practice was not there. So we thought we should try to see whether there are living where, you know, there is an unbroken tradition and people are making a living out of this by making agricultural implements, etc. So, and in the process, we went to several places, and it was a very tragic story. They will say, नहीं साहब, वो 10 साल पहले बंद कर दिया. It was no longer fact, you know, charcoal नहीं मिल रहा था. 3 साल पहले बंद कर दिया. And in several places the furnace was there. Say, नहीं, हम उसमें पूजा वूजा कर लेते हैं. So in one of the places I wanted to see this thing. नहीं, साफ ऑफ होगा. We were not used to it. It was very tragic, and at one of those places. Interesting thing like that. But finally we found this Ghatgaon Sela place, and then they were actually practicing. And there one of the farmers said that actually we prefer these fellows Fauda, you know, they are farmer Fauda, to one which is made in the factory. In the factory is Tata Steel, which is hardly 100 kilometers as the crow flies. They said, though these fellows, this thing is costlier to us. It may be because they are in a rocky land and this is made to their specifications, whatever it is. So the premium, they used to pay a premium on over the factory made agricultural instruments. So what is the reason? Anyway, so we really don't know much of the reason, but primarily it differs from the modern, this thing if you see. It is in the this is the iron that we got made. Basically, in the phosphorus is slightly higher, and this is the earlier analysis from the early 20th century. Phosphorus 0.15. These are the Delhi pillar analysis by Hadfield of Hadfield Steel Flame, and these were Indian analyses, and you will see the phosphorus is very high. And it's a very low carbon steel, but used for cutting purposes. If you see the properties, you know, it can have very good elongation, as well as decent yield strength for a plain carbon, low carbon steel. Okay. Though there is a large variation in the properties because it has not gone through a melting stage. The slag is primarily iron silicate slag. Major this thing. These are all other analyses of earlier times. So the question that we have to ask is, the analysis, if you see, the Delhi pillar analysis, which we say is about 1500 years old, and that of the Agaria iron that was made in front of us are more or less similar. That is one. Second thing is that, Delhi pillar analysis varies from point to point apparently. It's not uniform, as though it has been made from small lumps of iron. So it looks as though, we will see other evidences, it looks as though that this is the similar kind of process which was practiced all at that time. So that means they have maintained this tradition of the technology with very little degeneration, in spite of their socio-economic conditions becoming so poor. How did they do it? How did they achieve this excellence? And how did they maintain it? That is a question one would have. So you have to actually interact with them to believe, to see the passion that they have of this community which has for their profession. You look at their daily habits, you look at their culture, you look at their group identities, marriage rules, and so on, and you look at their gods and myths and so on. Everything is about iron. Nothing else. Everything about iron and iron making. That's what these people are. For example, these are hand bellows for making. Of course, this is not an iron smelting, but there are historical records. I have not seen it, but the larger furnaces of Hoshangabad, they had hand ones, whereas these are foot bellows fellows. So this bellows are called dhukan. So these are god dhukas. God means leg. So god dhukas and these are hat dhukas. They will not intermarry with each other. God dhukas, because you see this frequency of this operation is much lower than that of this. This I told you about 100 times, 120, 130 times a minute. And these are larger furnaces. Dimensions are different. So there is a difference in technology. So if a girl from here goes there and then mixes up the technology, there may be problems, So the god dhukas, and similarly, of course, see this way of putting this thing is, these are called the pathariyas. वो पत्थर में वो उसको stabilize करते हैं, blow pipes को. There are two of them. No? Whereas the other type where they will put small twigs and tie it down, they will not marry with each other. They are two different communities, and so on. And within the Adivasi, please remember, there is the other point which I was arguing there at the other time. The iron makers, the makers of iron, almost in all communities, are in the caste hierarchy. Not only the caste hierarchy, even in the trials, the interdining determines your caste hierarchy. Who will eat in whose house? Okay, so agariyas are the lowest of the low. And so also in the south, apparently, not the kamars. Please don't confuse lohars with loharas. These are loharas and asurs. They are asurs. Okay, their gods are not the Sanatani gods. They are Agnyasur, Koilasur, Agnyasur, and Lohasur. Of course, the highest one is Lohasur. So they call and their mythologies very clearly define their animosity with the Aryan gods and the Aryan heroes. For whatever reason, it is mutual because iron is not a very respected metal among the metal hierarchy. In many of the sacred these things, you can't use iron implements and vessels and so on. So, and in down south, as I was discussing with somebody, the fellows who make them are again very, very low in the hierarchy. Parayas apparently in Tamil Nadu, the iron smelters, not the karmakar, not the kamars or the lohars. Karmakaras as they're called. For example, in Karnataka, Kambara. Yes, the iron smiths are called kamars in Karnataka, whereas these fellows are called mudde kambars, the fellows who make the bloom. Mudde means, lump. Mudde kambars are lowest of the low. They are So there are very strict rules on mixing. So, and then you look at their love song. This is of course, it should be, this is a translation from Alvin. It should be in their language, in one of those karma songs or something. I wish somebody could sing this. This Azir boy says, come to the forest and cut a green tree, come to my bhatti and press the bellows. He tells his fiancée or whoever. And says, this girl says, press the bellows in the fort, slack comes flowing. Make me stay with you, I will stay in your Asur house. And then she says, he can cut trees, he can collect little honey. This Asur boy doesn't know how to beat the iron, and so on. See, about iron. See, everything is about iron. So, no wonder everybody else used to call the Agariyas are the dullest of the people. Because this is what, you go and talk to them, they only talk about iron. And you look at their myths, how do they codify their technological knowledges? The sun is their enemy. Sun is their enemy, so they will not work the bhatti in the daytime. Okay, you would think they are absolute obscurantist belief. क्यों करते हैं ऐसे? It's very difficult. See, as it is a marathon every day, running that bhatti, and you have to do it in the night, in the middle of the night. They actually, you know what do? They start, the first time I saw it was a great experience. We went to see them in this thing on top of a hill, so we started at 12 o'clock in the night from wherever we were staying, and then hiked up the hill. And we reached around 4 o'clock in the morning, and the bhatti was in full swing. And from a distance, you could hear that bhatti operation. 4 o'clock is the time when nature becomes quiet. Even the owls, etc., stop making sound. Just before the birds wake up again. There's a 3 to 4 o'clock, when very quiet. At that time, we were climbing up, and from this distance, this bhatti is operating. You can see you can hear the bellows only, no other sound. It was like some huge animal breathing or something. And as we go up, and then there's this light of the bhatti only, and this husband and wife lady and that boy, ghostly movement around. It was, the sun is their enemy. Why do they work like this? So they finish the operation. When they want the highest temperature is when they finish the operation, because they will take out, the slag should be molten, metal should not be. If the slag is slightly cold, one hammer and it breaks. Whereas you have to take it out quickly, you soft hammer for some time, squeeze out this thing, and then you consolidate it really with their big hammer, and you make it into a sound ingot, fairly sound ingot. Now what happens is, if you look at the humidity of the air through the day, I'm talking about absolute humidity, not the relative humidity. Here of course I'm plotting with relative humidity. The lowest moisture content in the air is just before sunlight, because dew has fallen. Dew has fallen, and once the sunlight comes, again the water vapor will go to the air, and the absolute humidity keeps on increasing. And anybody who has done some raceway flame temperature calculation for blast furnaces, you wouldn't have done it. You know that the temperature that you get from a flame, air-blown flame, in a charcoal furnace or a coal furnace, is dependent on moisture. Higher the moisture, so for example, in the blast furnace, he wants to decrease the temperature of the blast furnace, he will humidify the blast. You dry the blast up, and then you'll get higher temperature, and so on. So if they want the highest temperature, that is the time to finish, when it's just before sunrise. That is why they work in the night. So they have codified this knowledge, because they don't have a dehumidifier, they don't have a preheater. Okay, so, and you see the temperature difference, that's the relative humidity comes down from, oh my goodness, where did I go? Yeah, so as the relative humidity comes down from, let's say, 80% to 40%, that is almost half, 80% to half, yeah, half of it, the temperature can come down, the temperature can increase by almost 100 degrees. And it's about 1475 degrees that you need, you know. And that is why also they work very well in winter. Though winter temperature is lower, but the humidity is absolutely low, 20%, 25%, and so on, even less than that. Whereas in summer, it is 85%, and the temperature is high, absolute humidity is very high. So they make their iron in this thing, and it works with the farming activity, because in summer when they do the farming, these fellows are free to do the smithy operation, repair the tools, and so on. So it matches with the farming community. But then this has led to people being called, you know, most of the British surveyors called these agarias are the laziest of the people. Why? Because whenever they visited in the daytime, and the agaria is sleeping. Agaria and Agarain, both of them are sleeping because they have worked so hard the night, whereas these fellows are called the lazy Agarias. And then they use this bellows. And we asked them, why don't you use, you know, hand bellows are already become very, very, you know, har kalai wala, you know the kalai, you know, tinning guys. Those were the days when copper vessels were tinned. Those fellows were all using hand bellows. Why don't you use it? He said, नहीं काम नहीं करेगा. वो स्मिथी में चलेगा, you know, उसमें चलेगा, यहाँ नहीं चलेगा, भट्टी में नहीं चलेगा. So this was another thing. Of course, everybody suggested, no, this again, these were all ignorant guys. Then somehow I was convinced that there may be something in it. If they are so vehement. Actually, I saw one of those families, the young boy, and the mother was showing. The mother said, नहीं हम भट्टी नहीं चला रहे हैं, लेकिन आप आइए यहाँ देखिए. She had a son, her husband was dead, so she was supported by the son. Son was only 16 or 17-year-old. And she showed me, kya hai? She made himself a hand blower. Using the convolute was made out of pottery and cycle equipment, and you know, and a little bit of fabrication himself. He had made it. He uses it in the smithy. So they were aware of the. And you know, they were creative enough to make their own, but they wouldn't do. So then we could in our furnace, because we were using contraptions. So with our valve operated with the relay, we could either switch from continuous flow to this thing. So we have to make sure that in both the cases the amount of air flown is the same. And you see this operation is going on. This is the temperature just in front of the two. This is open, so we could use a 2-color pyrometer to look at inside and measure the temperature. And that's the temperature measurement. So here we are doing bellow kind of a simulation. That kind of temperature is here. And then we go to continuous operation, temperatures come down. Okay, and then of course if you have a heat transfer, mass transfer background, you understand that if you pulse, that means you are continuously changing the fluid flow. So you go to a transient modes of heat transfers are always much higher than continuous modes of heat transfer. You know, transient modes are always higher than you. If you have lit a firewood oven and blown, try to bring the fire, you would know what works better. You know, what works better. So, and then I had an MTech student and we wanted to try, he was doing some limestone calcination in a packed bed, of course not in the bhatti, but a calcination. So that also has a blow of air burning the coke breeze that is mixed with limestone. This is with steady operation, percent dissociation, and this is of course at various temperatures. And you see the band is here. And we shifted for the same amount of amount of air blown, periodic operation, the band went up by almost 10% dissociation, and showing that this really improves the process. If you come back to this, yeah, this is what I wanted to show. This is the cut section of this. One of this expanded. You see that this is actually the dark pillar has been made through these small pieces forged together. So each of them is probably 5 kg, 4 kg, which is the typical of the bhatti, which is I'm talking about the 20th century, 21st century bhatti compared to this 13th, 14th century, 12th century piece. So very similar technology, and people hypothesize that even Delhi pillar is made this way. There are some theories as to how they made. Delhi pillar wonder is not that they have made such huge object. It was the largest piece of iron object anywhere in the world at that time. 5th century AD, largest piece. Interesting actually, such a huge, difficult process. And you make this useless stuff because some king wanted to declare that he is very, but they made. Anyway, king had the money and people are ready to work. Beg your pardon?
It's a matter of death. How to
Life and death, he says.
Yeah.
Life, stays on the whims of king actually.
Yeah, that's right. I know. That's why they're kings, no? They can always say, off your head.
Yes.
Yeah. So they made it because this had no purpose other than decorative purpose, or in this case, this is probably a deepest thumb. So it had a purpose of whatever, religious significance. There was no strength involved in this. So this is the technology. They put the lumps together, hammered them together. Delhi pillar, of course, I don't know how they got that nice surface, which is absolutely beautiful. Beautiful surface, and you see the capstone. It's all done. Such a nice work. I don't know how they did it at 500 BC. Even now, if you ask forging companies to do it, they'll find it difficult. Tata Steel they have one there, but that is cast.
One inside enamel also.
But those are all cast. Yeah, that's right. Forging is difficult. But when they came to making the Konark pillar, this is load bearing. They didn't use this. You see this. This is a composite made of bars, So they first forged the bars and then put them together. So the technology is different. The Konark bars as well as, and so on. So, and this, of course, is a wonder. This, if you see, has 3 layers. It has 3 layers. Inside one, this is probably steel, this is probably bronze, and these are steel rings outside. To stop this thing from bursting. One of the biggest problems for the cannon was you fill this thing, lot of this thing, and then you set fire and it bursts and kills the fellows. Whereas this is reinforced with, the whole thing is reinforced. So it's an entirely different technology. Of course, this is 14th century. So, in conclusion, I want to say that enriching, it's very enriching to dialogue with people's knowledge, as against written down knowledge, which has been documented and so on. People's knowledge, which can be very highly enriching. And we learned a lot. This led to 2 of my PhDs using this periodic flow in some heat transfer measurements and some iron ore nickel ore reduction kind of a thing. 2 PhDs and 2 or 3 MTechs came out of this. Nothing to do with the iron smelting. What we learned, the principles we learned, which we used for our modern research. Okay, so it can be very enriching if you are ready to explore it with humility. we should remember that it's a different epistemology. You can't be looking at with your tinted glasses at their technology. Then you can only call them obscurantist and ignorant and so on. Of course, this is the story I'm not going to tell, which is because we have not worked on this. Nobody has worked in recent times, which is this magnificent swords from Indian steel. I don't know whether still people are there. For a long time, people didn't know probably that it's from India. So these used to be made, swords used to be made in Damascus and sold in Europe. And many European heads were rolled off with those swords. Unfortunately, it was from India, apparently. The steel was from India because these Arabs were great traders. They used to come to Hindwani, as they used to call us. They only called us Hindus. So Hindwani, and buy these ingots of Indians were semi-finished products. We were very happy to export raw material, or even now, just like now in those days. So they would take them and make them into, they were excellent smiths in the Arab world. So they would go, apparently stand in the plaza in the Vienna. Vienna was at one time the cultural capital of Europe, and they would stand in the corner and throw a muslin handkerchief, again made from India, and throw it and cut it in the air. It's so sharp, and that's how they used to show, display and sell. It's so sharp, such a sharpness. And then the quality, the quality of the fame of this also is because of this, what is called the Damascene pattern. See, this is not decoration. This is not artificially made. This is natural to this. And this is the width of the fold. So this is macroscopically, you see this pattern on the sword. And this is cementite. Such macroscopic. And we are talking about this sword, which needs to be absolutely not only hard and tough, because you can't have thing which maybe however hard it is, and this thing, if it breaks, you're dead, isn't it? So it is, so the wonder is, with this coarse cementite, how did you get the toughness? Okay, how do you get this coarseness in the first place? How do you cast a 1% carbon, this is about 0.8, 0.9% carbon, made in crucible. How do you make this and get such coarse cementite? Okay, this is not heat treated over some 7 days or 10 days or 15 days or something. It's just melted and cast. Only thing is it is solidified inside this thing. He will stop the operation, wait for 3-4 hours till the liquid stops this thing. And then these fellows will work it such that they get this. These are called steps of Muhammad. So if a log sword has 40 steps of Muhammad, that is the highest quality of the wood's blade, Damascene sword, that they will be selling in Europe. And so on. So you have, there are legends about Tipu's sword being like this. This was so popular that all so-called royal societies in England, in Europe, England, Germany, France, everybody set up royal commissions to understand what is this woods, including Humphrey Davy. Humphrey Davy was given the commission, and he used the whole periodic table, put it into iron to try to get this property, apparently. This is what he says, and you have to see his report. He had no clue as to what happened. You have to heat it like this, and if you heat slightly higher, everything is lost, and so on. Yeah. And you will see that lot of fake fellows made money out of this what are called the pattern welded. You mix different sheets of metal, put them together, and then confuse the microstructure so that, and so on. So, yeah, the ingot itself, you can see the cementite plates. Unfortunately, we have very little information about how this process is. In the late 90s, 80s, 90s, in California, this Verhoeven did a lot of experiments trying to get these properties. It's a very Sherby, yeah. Verhoeven and Sherby, they got some very good. See, this was also superplastic at medium temperatures. At this thing, so he got some properties, but never the microstructure so far. It's an interesting process. Of course, Professor Manna said it's a simultaneous smelting operation to get woods. I disagree. The only reports that we have on the woods process is by two European travelers. One is Voisev of the Hyderabad process, and there is Buchanan of the Mysore process, Mysore-Salem process. He was traveling all over south. And in both of them, it is iron made with the bhatti, then put it into a crucible, along with some interesting ingredients. The crucible itself is a very, very interesting crucible. And they put bark of Cassia auriculata. In Tamil, you call it avaram. And then leaves of Laurifolia gigantea, which is a milkweed kind of a shrub used in medicine and also in worship. It's called arka. Ekka in Kannada, ekkam I think in Tamil. It's a milk, it has a violet kind of flower. That all were put together and then blown with closed condition. That's why it's called ukku. Urukku from that woods comes. Ukku in Kannada would mean, one is ugihaku, that means asphyxiate. Another is boil over. So in both sense, in Urukku also probably means boiling or something. I don't know.
It means the melting.
Melting. Is it okay? Yeah.
Telugu it means Telugu word is ukku.
Yeah, ukku. Yeah, that is right. But from that, but the etymology when I was trying to see ukku's etymology, it has ugihaku or ugisu. Ugisu steam it. So those leaves may be doing something with it. Yeah. Anyway. So these are all the acknowledgements. The Asurs of Bishunpur and Ghatgaon and Agariyas, the water of Nagar. These fellows came to IIT Bombay, spent some 15 days setting up the furnace. And these were my colleagues in this whole effort. These were my students who worked, and these are, of course, IIT Bombay colleagues who worked with this. And Dharampal ji, I don't know whether you've heard of him. Have you heard, you students should read this book called The 18th Century Science and Technology of India by Dharampal. Okay? He has not written it, he has just collected British records of the 18th century. And it's a wonderful, inspirational book to see how great our yes, technology. It's not about iron and steel alone. It's about plastic surgery, and it's about agriculture, and it's about mathematics, and it's about astronomy and so on. So it's a great book. Thank you. So all good photographs are by my student Shirish Wagulde, who did PhD with me. But most of the time he spent in things like this. He spent 1 month among the Agariyas and several months running after tigers. He took the photographs. Some bad photographs that you see is by me. I'm not a photographer. Thank you. Do you have time for questions? Or?
Yeah, so
it's very late. Yeah.
Thank you, Professor Ballal. So just please a couple of questions. Yeah.
Two things I wanted to know. Is it that Agariyas were always making only bloom? And if so?
No. They will also make agricultural implements. All those they will make.
But smaller items, how were they cutting the bloom?
With their own axes.
But
iron axes. When it's hot, they cut it. Actually, as soon as the ingot is made, as soon as the bloom comes out, they will hammer and make it slightly longer and cut it into small pieces depending on what they want to make. If they want to make some hammer or small tools,
Yeah.
they would make it immediately break it into pieces.
So it is always the same bloom which they produced in an earlier time,
Yeah, they
which
keep
they
it.
were putting it as an axe. That's what you mean?
Yeah.
Okay.
You see, iron could be forge welded, so
Yeah.
they will make a hole and they will make it around and make that.
But if I want to make it into some 10 pieces,
They would forge it together.
they would forge.
They can forge it. This is the advantage of iron. No? See, iron
but
suddenly
one-
became.
One bloom which they produced, if they want to make it into 4 pieces or 5 pieces,
They cut with an axe. I've
Axe.
seen them cut. Yeah.
you have seen. But
Yeah.
that is what you have seen is in present day. But ancient
Olden
times,
days, we don't know.
we don't.
Sir, locally they hammer and reduce the cross-section very slowly.
The cross section is one, but when it's very hot, they take it and with a cold steel axe. Yeah, hot condition only they can
Yeah.
cut.
Second question is related to the Konark pillars or even the iron pillar. Particularly come back to Konark pillar. How were they forging? Each ingot that you have shown is only just of this size. So several such ingots, they have to bring it in hot condition and then keep building that entire length. How
Yeah,
is it?
I think the great advantage is that iron is a poor conductor of heat compared to copper.
Yes.
So locally you can heat without heating the rest. So they must be having some kind of thing. I don't know whether it's vertical or horizontal. In Konark it must be horizontal. So locally they will hammer and join them. Probably made a batch and then locally they will hammer and join. This is what I'm guessing.
Local blowers.
There will be several.
Not allowed, no?
I think some pictorial representation is there.
No. They will be putting their bellows on both sides. Put charcoal on top and blow.
Because
Yeah, in situ heat.
Heating is done.
Yeah.
in situ,
This is what is proposed for Delhi pillar. Delhi pillar, they say two mounts, and then one side you make the iron into hot condition. Here also on top of the pillar you bring it and build it a little bit, and then you put a little more mud and then build it.
yeah.
That's what they must be doing. I don't know. I'm hypothesizing.
Delhi is done in horizontal. I like that.
Yeah.
I just have a comment and a question.
That's all hypothesis, sir. You are saying hypothesis. Somebody else says vertical.
This is not a hypothesis. You will see those papers.
Papers, yes, but who has seen 1500 years ago?
No. The way the letters or alphabets have been actually struck.
No, that has been done.
The interface we have.
Interfaces.
Yeah, and also that
happens is
smoothness of Delhi pillar is
writing
different
the
from
letters,
Konark
alphabets.
pillars.
Yeah,
Konark pillar
Konark
is,
and Dhar
rectangular or cross.
are not very smooth at all.
Yeah, they are not smooth and
Smooth
also
because
you can
that is
see
not the decoration was not their
You
purpose.
will cover that.
it's a real marvel. Thank you.
Lot of questions, but
My comment is that we were stressing about the lack of the literature description. Of course, people then did not realize that in 21st century we'll be looking at these processes in a detail. So they were not creating thing for our consumption now. The related comment is that even in the mathematics, a lot of things were written in a very cryptic way. Like the Pascal's triangle just was written as Pare Purnam, Pare
No,
Purnam.
that is okay. That's okay.
800
But it
years.
is written. But some of these things are not written at all.
That we may discuss it, why it was not written, that I have a different hypothesis for that. My question is, on this caste hierarchy that you were talking about, are there any written texts from where do we learn this caste hierarchy about these tribes, iron tribes related to the iron making?
Where did I learn?
Where did normally we learn about them?
I don't know. I talk to these people. When I talk to these people, they say, नहीं, हम तो गांव के बाहर रहते हैं. हमारा his houses, every village or every cluster of 5-6 villages will have 2-3 agarias who will serve the agricultural community. They will make the iron. That's
Inside the village or they are ostracized?
they are on the periphery, not outside. They are on
so-
the periphery. That's what they told me.
The
That,
Dokra casting people, all the Dokra casters all over India, They are not, they are not allowed to mingle inside the villages, so they would stay.
They were, for example, will dine with the buyers,
I kindly
but
request.
not with somebody else, Gonds or something.
Yeah, so we are running out of the time, so we have again the panel discussion. So with the same topic, we will continue again. So we have a discussion now. So now I request Dr. Venkatraman. Welcome again. So we have the second panel discussion, and that is on metallurgy of iron and steel, key learnings from ancestors and path forward. So our first panelist member is Professor Mohanty. He is actually BTech and MTech in metallurgical engineering from IIT Kharagpur and PhD in materials engineering from University of Karlsruhe, Germany, and did a course in business administration from France. So he served as a professor at IIT Kharagpur, director level scientist at CSR NML, Jamshedpur, and as well as the director R&D at Tata Steel, Tata Research Professor at IIT Kharagpur, and Vice Chancellor of Biju Patnaik University of Technology, Odisha, before taking up the current position in 2010. So he is also the adjunct professor, IIT Bhubaneswar, and honorary scientist at CSR Institute of Minerals and Materials Technology, Bhubaneswar. So he has a lot of publication in this field, and I welcome him. Yeah, so I welcome him to the panel. Yeah, thank you, sir. So we have another panel member, Professor Ballal. So I think we don't require any introduction. So he has given a wonderful talk today. So I request him also to on the dais. So we have the another member, Professor T. Jaykumar. So he is Director of Metallurgy and Materials Group, IGCAR Kalpakam. So Professor and Dean at Homi Bhabha National Institute. And he did his PhD in engineering faculty from the Germany in 1996. He has published more than 350 journal articles. So I request him to be on the dais. Thank you, sir. So I request another panel member, Commander S.K. Mishra. So he is a mechanical engineering gold medalist from the Government College of Engineering, Jabalpur. He is advanced postgraduate course in controls and systems engineering, passed from the University of Cambridge, UK in 1974. PG DIP in finance management from University of Bombay in 1986. So he has more than 40 years of rich professional experiences at various organizations. So he has a lot of experience, including the assessments as a business profit center head of a corporate companies and many other. So I also welcome him to be on the dais. So now our another panel member, Professor Vinod Kumar. So he is the head of the department and associate professor in metallurgy engineering and material science department, IIT Indore. So he has completed his PhD and MTech in materials engineering, material science and engineering from IIT Kanpur. He was adjunct faculty in Materials Research Center at NMIT Jaipur. He has also received the Young Scientist Awards from other organizations. So he has published more than 65 plus research articles in high impact journals. So I also welcome him on the dais. So with this, so we have the wonderful discussion on this topic, because as I mentioned by Professor Manna, steel is something very crucial for the economy of any country, so including ours. So we have now the brainstorming session. So I request to all panel members, due to the time constraint, so not to exceed more than 10 minutes. So that will I appreciate. So now I request Professor Mohanty to begin with.
So there is a special request from organizing team to all our esteemed panel members, that please excuse us because of the delay. We have to conclude this session somehow fastly, and because of that we only allow 10 minutes to present, and this discussion part we will start. But since family members are waiting outside for cultural program, students are waiting outside for cultural program, so we have to finish this session as soon as possible. And discussion part, I am hopeful that it will continue even beyond tomorrow also. Thank you, sir. Please, sir, Mohanty, sir, this is your turn now.
10 minutes you said, no? Presentation. I have a presentation. So, good evening, everyone. And that's the... Not before that. Good evening, everyone. Actually, there are there's about 10, 15 people. So therefore, all of you can come a little closer, please. There are only 5 people sitting there, young people, who can come closer. So this is the risk of speaking in the last session, because since we didn't control time, so we have to, so we will go quickly. Which one? HTML. You have to remove this. Oh, from there he's doing. Okay. While the screen is being changed, all I wanted to say is 10 minutes is the time. I will stick to that. Basically, all I'm trying to say is this is the session which is on iron and steel. And I have another lecture where they say that I'm supposed to be speaking also on the ancient ferrous and non-ferrous. So let me quickly tell you that what I am not covering. What I am not covering is actually basically Damascus swords, the woods and Damascus swords, because huge amount of work has been going on in the past 10 years in this area. And the Konark iron beam in which we are working currently, and huge amount on the Damascus swords, because probably this is the only ancient area of iron making, or the high carbon crucible iron, which is alive today. Today, in the sense, there are nanostructured materials, they say nanocarbon also in the Damascus swords, to 3D printing and producing Damascus swords. All these have happened in the past 2 years. So I shall not be talking about it. Konark also I will not be talking. So I will quickly go through, and since my friend Dr. Jaikumar is going to talk about the iron making, particularly Delhi iron pillar, I will not go through this. All I wanted to say is the iron making technology in India, when we talk of what Professor Ballal says, I want to echo that, that the humility part is extremely important. Anuradha is here, the only one who would have seen that the African iron making, which is what I always teach, today there are YouTube iron makings of Burkina Faso. I didn't know even the country's name, that such a country exists. But in Western Africa, Burkina Faso, the iron making technology is 2,500 years old. So it's not just the Indians or not just the Chinese who have been doing this. A lot of other countries also have been doing. So the humility part is very important. So continuing where Professor Ballal has left, low humidity and high humility. So this is what is very important. Yes, I'll make it full. Thank you, thank you. But when we talk of iron making, unfortunately young students are not here. When we talk of iron pillars, or pillars actually, many students basically, they would make a confusion with the iron pillar and Ashokan pillar. And they all say, pillar idhar bhi hai, Ashokan pillar theek hai, ye sab. But the point is, the Ashokan pillars are all stone pillars, and from Vaishali to, I think it's not coming on the screen. So therefore, our friends over here, you can't see anything. So either one has to shift to that place.
I think this is like lecture only, so we'll sit there. And
Yes, yes, yes. I think that's much better.
This is not a panel discussion.
It's not that kind. So we can always go there. So if you are talking of the Ashokan pillar, there are only 20 Ashokan pillars which are known to survive. And the most famous among the Ashokan pillars, of course, we all know, is the Sarnath Ashokan pillar. That's the pillar which is what has been accepted by as the national emblem of India. The 4 lions and the 3 of them we can see at a time. So Ashoka Chakra is from that. So tradition of iron making, steel making is pretty old. We know that now. We have listened to that. But actually, how did man know about the iron? Of course, from the meteoritic iron, that's known in many places. If you go to British Museum, you will see the meteoritic iron. They have named them also of various sizes, etc. Timeline, I think Dr. Manna was showing part of that. But 1100 BC needs to be corrected. Probably in India also it could go up to about 2000 BC or so. There are many places in India which are newer places are coming up. But more important is here actually, 12th century AD, the export of iron and steel from Malabar was already taking place. That's what I wanted to quickly say. And I don't intend to read that. Suffice it to say that I think 2004, 2.4 million ton Tata Steel acquired. We acquired a steel company in Holland and in England, which was about 10 times higher. So overnight they became very large. So now what Professor Ballal showed, the bloomery process of solid state iron making, basically our people are not using the limestone, so fine iron ore, charcoal. So you make actually a semi-solid fused mass because your slag has formed, which is liquid, and expel the liquid slag. But even then, you will always be left with slag. This is the interesting aspect. All bloomery process iron making, from Africa to Europe to India, bloomery process iron making, whether it is Delhi iron pillar or even Konark iron beam, what we have seen is this kind of thing. So I will not get into the details, but we have seen actually iron broom just removed from the furnace. In NML, Professor Ballal may have gone there when Professor Ramchandra Rao was the director. A number of people from all over India, they came with the Swedish, I think, collaboration. They made a 3-day ancient iron making process which were replicated there. I'm not getting into that. So preparation of charcoal, etc., that's not important. So I'll quickly breeze through this. The most important thing is about Delhi iron pillar. Hadfield actually himself saw it in 1912. So everything that the Englishman sees, he discovers. So you go to Livingstone in Africa, the waterfall, so they discover, and they call it Livingstone. But actually the Africans have a different name for that for centuries. So similarly also here, the Delhi iron pillar is existing for 1600 years, and Hadfield actually discovered it. As a result of that, what happened? In 2012, they were celebrating the 100 years of that. But that's not a bad thing actually, because the American Society of Metals, as a tribute to the mankind's contribution to science, they said, let us donate a plaque to the Delhi iron pillar. So the ASM iron pillar, the plaque actually came to the Delhi iron pillar. I've seen that. Where it is kept today, I do not know. And not just that. The interesting aspect is, since Qutub Minar is only a few feet away, people go there, spend their whole day in Qutub Minar without knowing that actual Delhi iron pillar is sitting there, and Qutub Minar may be 250 years old, and this is 1600 years. They come back quite satisfied. It's almost like going very close to Bhubaneswar, where Anuradha may have been, where Ashoka's, the inscriptions are there underneath. It's about 2,500 years or 3,000 years old, but they will go to the mountain top where the Japanese built the temple only 50 years back. And they said, we have seen Dhauligiri. but actually 50 years. So this is another thing I thought people should know about it. The dimensions of iron pillar, it's all known, corrosion resistant part is known, but equally important is this. Some of the logic of horizontal or the vertical part, when Professor Anantharaman wrote his book, the rustless wonder that India was, that was the book which was called. But thereafter a number of books have been written on that, but maximum contribution has been done by Bala in IIT Kanpur. But one of the things, whether it is horizontal or vertical, I'm quite sure Dr. Jayakumar will show more evidences, but when you actually put these alphabets, when you put the manner in which you are putting the letter, there will be portions which will chip off. So the directions from where it is chipping off, Bala's arguments were that they were actually horizontal and then made vertical. So I will not get into the original, but a lot of data he has given why. But equally important is why this was there. It was not there in Delhi, of course, in the first place. It was there in Udaygiri. So I am extremely fortunate, and this is the first time I am coming to Udaygiri. So the Malwa area, actually the capital of iron making in India. And all iron pillars, out of the 4 which have been discovered so far, 3 iron pillars are in this area only. And even the Delhi iron pillar is from Udaygiri. And how during the summer solstice, in the Vishnu Mandir, just in front of that, the shadow used to fall. That is why it was there. It was not without any purpose. Anyway, so the original location of the pillar, the Vishnu Padagiri, identified Madan Udaygiri. It's in the close vicinity of etc. etc. I think Venkataramanji, Dr. Venkataraman knows that already. So this is the manufacturing process, as you'll find in some of the books. These are published in several kinds of publications. So I'm not getting into that, how the furnace was there, how the handling of the clamps were there. So this is how it was there. So the method of manufacturing of DIP, there are papers and papers. So absence of calcium oxide, but I will come to so the entire thing is centriforging actually. Basically it is centriforging. Now when you talk of the Bloomery iron and Delhi iron pillar composition changes because of the ore from which you have brought it, it's not the same place. And by the time you are doing it part by part, obviously the composition is different. So the phosphorus is high, and I have told in the morning why the phosphorus is high. Because we are not doing any dephosphorization. And so the phosphorus comes 50% from the ore, 50% from the coal or coke, as we suffer from the phosphorus in Tata Steel or all the steel plants. So the phosphorus was not being removed here. But the point is that if you put copper and phosphorus, the corrosion resistance in normal steels also improves. So we call them the corrosion resistant steels in the modern times in the 40s. This is, of course, Balasubramanian's work. So according to him, the iron hydrogen phosphate hydrate and the amorphous delta FeOH layer which is there. So this is what actually contributed to the corrosion resistance. But actually, the subsequent work by, as I will show here, by Kamachi Muddali and Baldev Raj from your laboratory, Dr. Jayakumar, the in situ electrochemical behavior was done and published also. This is an excellent paper on corrosion and composition of the Delhi iron pillar. But for the first time this was done. But more important part is that if you compare with the Armco iron, which is also polished, and the Delhi iron pillar at different heights, you'll find here at 0.5 meters, 1.29 meters, etc., etc. So you'll find basically the electrochemical behavior is quite different at different heights. So iron pillar thus symbolizes or symbolically represents the true Indian philosophy, etc. That's not very important. So if you go through Kamachi Muddali and Baldev Raj's work, you'll find that basically whether it's a purity of iron or alternate wet and dry process, initially formed gamma FeOH which is converted to alpha FeOH, oxygen's diffusion and the rust process. With all that, basically Delhi's distance from the seashore A and the wet and dry alternate positions, this is attributed to the corrosion resistance. And most important part, I think the work from Kalpakam showed that the top portion of the Delhi iron pillar actually corroded extremely fast. And those data are all there, but I think there is no need for me to go through that. The iron pillar I always love this iron pillar, the description. I've never been. Dr. Venkataraman says I would have taken you. Why do I say so? Because I'll quickly go through the Dhara iron pillar. Because if you combine the three pieces, it is 43 feet, more than 43 feet. And Delhi iron pillar is 23 feet. If you combine them all, the total weight is 7.3 tons. And if you put the missing part, probably it will become 7.5 tons. So it is heavier than Delhi iron pillar and taller than also Delhi iron pillar. So these are some of the historical facts, but I will not go through that. But near Lat Masjid, I think next time, this is where the Dhara iron pillar is there. So this is where the iron pillar. But more important is, this was during the olden times, this is where the pillar was actually lying. But later on, I think our superintendent of ASI of this area, he has left meanwhile. Thanks to their work, they actually brought it in this manner, which is what Professor Ballal also showed. But the beauty part of it, that the fragments set in the position in 1980s only. Before they were all there in that position. Some of them are missing. So they are all collected. One part is still missing. The beauty is that this is octagonal part. Look at the forging of the octagonal part. Yes, 2 minutes. Another 2 minutes. So dimensions are all there. The Sivaling part and the top portion. Another important part, this is I think about the Dhara iron pillar, it was not actually buried. It was not buried. That's the reason why actually it fell down. It was all balanced with very heavy weights. And how the wear was put, how the hole was put is very interesting. So we started teaching some of these in IIT Bhubaneswar and parts of that in IIT Kharagpur also. That the manufacturing process of Delhi iron pillar and the Dhara iron pillar, how they are different, etc. The Dhara iron pillar, how pieces were, some of them of course is speculation. So I will come to the end of that potential dynamic potential, I think it's not necessary. Mandu iron pillar is the next one, that also is not very far from here, near Jami Masjid in Mandu. And the Kodachadri. So what I wanted to tell you is analysis of these small samples. Basically you will find the slag inclusions are all there. And the cannons, this cannon in Thanjavur is supposed to be the heaviest cannon in India. Probably Asia, they said. 8 meters long, 22 tons. So Thanjavur cannon, some details. And the composition, here it is much cleaner actually, because the process is slightly different. I am not getting into that. Corrosion behavior. And Dalmandal cannon, this is in West Bengal, also is pretty big, 3.8 and 20 tons is the... So I will come to the summary of the observations. Iron pillars represent a great legacy without doubt, and the pillars represent the shining examples of the structures. And they necessitate, of course, deeper studies also, although we have a great amount of studies. And more sophisticated techniques. Tomorrow I am going to show how Newton refraction of some of the Damascus swords in recent times, they throw completely different kind of information on the Damascus swords, beyond what we have done also at NML or anywhere else. Thank you very much.
Thank you, sir. So now I request Professor Jay Kumar.
So I will take this out. This one I am taking out.
Okay. So, good evening to all of you.
Yeah, it's now there.
Good evening to all of you. Okay. Good evening to all of you. First of all, I would like to thank the organizers, in particular Dr. Professor Ishwar Prasad for inviting me and tell you about few of the things what we have done on both Delhi iron pillar and Kutichadri iron pillar. Because of the limited time, I will try, and also because some introduction is already given about these iron pillars, I will try to be brief, and then I will try to explain the work what we have done. In one case, we demonstrate that the pillar is made in the horizontal fashion, and also the interlocking of the lumps which are made in small quantities. Some time back it was told 5 to 6 kg, but we believe that this may be around 20 kgs in the case of Delhi iron pillar. And also, we also take that the locking mechanism also is taken from the natural rock structures. So this is one aspect which we would like to bring out. And also in the Delhi iron pillar, we feel that there is gold at one of the regions. That also I will show you that how we have interpreted this. And also the thermomechanical processing, it would have gone through at different regions, and the structures what you see through in situ metallography, that also indicates that the temperatures and strains and the cooling rates, in addition to the composition variation from place to place, would have played significant role with respect to the microstructures those are generated. But at the same time, I would like to say that the corrosion resistance might not be having to do much with the microstructures rather than the phosphorus. And one more point we would like to bring out is that many of the people interpreted on the samples that the needle-like structure, what they see, they consider as phosphorus related. But we also, this is an indirect evidence, not direct evidence, that these are cementite needles. Okay, so with that I will start my presentation. So here on, no? Okay. So anyhow, I cannot go to all this, so sorry for that. Okay, this is a Delhi iron pillar. So we use number of investigations. These include visual inspection, dimensional measurement, X-ray fluorescence, in situ metallography, in situ hardness, ultrasonic and impact non-destructive testing, and the gamma radiography. And particularly the gamma radiography has been done in the night because of the hazards involved, and also to see that the visitors are not affected by these investigations. Now, if you see that the microstructures, what you see in different places, so here the height-wise and then the location-wise, it is given where the microstructures have been taken. But more importantly, if you see that in the Bastar, where the iron is also made, you can see that the Adivasi iron is the Bastar iron, and the Delhi iron pillar microstructure is shown on the right top. And here you see a modern ferritic stainless steel, where from the electron microscopy you can identify the possible orientations of the cementite, and if you align the grains in a particular orientation, there would be a one-to-one correlation about the cementite, which is identified through electron microscope of the modern steel in the ferrite matrix, and the orientations would exactly match. So from the orientation relations, so this is the indirect evidence, what I was talking. So it is cementite and not related to the phosphorus. But phosphorus is more uniformly distributed, we believe, in the matrix, and that is giving the corrosion resistance. And if I arrange these microstructures in a particular fashion, notwithstanding the location and locations, you can see that when we go from left to right, so there is a increasing temperature and slow cooling rate for the corresponding microstructures. You can see the continuous variation in the different types of microstructures what are obtained depending on the temperature, cooling rate, strains, how much strains it is given, that is how much hammering is done. So that means there is quite a bit of variation without much robustness of the process because they won't have the much knowledge, but it is more integrating it without any difficulty. And I think one of it is shown, the horizontal one is shown by Professor O.N. Mohanty, and there are two schools of thought, there are two schools of thought, whether it is made in horizontal or vertical fashion, and we would say that it is done through the horizontal fashion. That is essentially because when you do the hammering on the horizontal fashion, So you will see the interfaces in the circumferential axial orientation. Whereas if you do the pillar in this fashion, all the interfaces between the lumps would be in the radial circumferential direction. So what is done is that when you do the radiography, okay, I'll use the hand, no problem. So when you use the radiography, it got stuck. Okay, great. So when you do that, you can see that the orientations of the interface, this is in the axial direction of the pillar. You see that these are all axial and then circumferentially oriented. So if the interface is not like that, you won't see the contrast from the radiography. That is one aspect. And then in one of the regions of the iron pillar, you can see that the white contrast in the radiograph means the metal is heavy compared to the remaining regions, and that's why X-rays are absorbed in that region, because X-ray absorption is directly related to the atomic weight. So we believe that there is some material which is denser than the iron. Only that much we can tell. But further, it is only a guesswork that it is silver or gold. So normally gold is used in many places. So it is in the even bronzes, etc. So we believe that it is a gold which is there inside the iron pillar. If it is a void or something, means you will see dark. So that is another point which I would like to say. Third is that locking of the lumps. When we see this orientation, it's only I am showing it pictorially as one image, but there are number of radiographs. Invariably in every radiograph you can see that the locking mechanism of the one lump to the other, the shapes are similar to the way we see these rock structures, natural rock structures. So that is another point which we would like to say, that they have taken the nature as the basis so that it is becoming more stable. Whereas in the case of Dhar pillar, most likely they would not have followed. You can also see that horizontal, more plate-like things. So that is the way the Dhar pillar would have broken. But see, there are certain things when I say are direct evidence, there are a few things where we say inference. So that is subjective. But we believe that what we are speaking is more or less true. But that is subjective to different people. And one more point we would like to say is that in the bell region, the top bell region, one portion is cast structure. It is not the solid state reduction process. And this must have been added subsequently. And there is also a hole. So there I feel that they wanted to fix some idol or something, but which they have not completed. So that way also it is an incomplete thing. So these are some of the points which we have brought out from our study. So in essence, that at least we could bring out a few points. At least we could bring out a few points from these investigations, and some of the unresolved points have been brought out. So that is with respect to that. And this is the Kodachadri iron pillar. I think already the information is already given with respect to this pillar about dimensions, etc. This cross section is relatively small, and we have taken some studies here also from different portions. And then if you see, the corrosion rate varies from bottom to top. In the top region, the corrosion is very high, whereas as you come down, the corrosion rate is low. That is one point. Another is this pillar is a square cross section, and the pillar which this side which is exposed to the Arabian Sea, the west side, that has the highest corrosion, whereas if you see the face on the eastern side, it's almost very small corrosion. So there is a tremendous difference with respect to the corrosion from the facing and also from the height, because the height is more means directly the sea breeze is coming, and then it is having a more corrosion effect, whereas the lower portions. I will stop even now, no issue for me. So you can decide. Okay, so we have done a lot of work. So this you can see that in the west region the corrosion is more, and as you come to the opposite direction, particularly the east one, almost very small extent of corrosion. Another thing is, this is also done by forging, but so if you see that, structure, you can see very clearly the hammering and then does it work? Okay, so you can see that okay, so you can see the spread of that forged material which is coming out. So this is also done by forging, but whether it is done horizontally, vertically, that I would not be able to tell from the studies what we have done. Okay, so here also the microstructure varies quite a bit, and it also has the ferrite and then perlite structures. And here we have also taken a small piece from this pillar because it is too much rusted, and then you can take with from hand itself, some piece would come out. So, and then we did the investigations, we did various elemental analysis and all, and you can see that there are some carbides, that is the cementite, and also we have calcium based slag inclusions, what you can see. So this is again a ferrite perlite structure with slag and also the carbide precipitates, what you can see here. And if you see the hardness variation and the composition of the carbon which we have taken based on the ferrite perlite percentages, and the expected hardness taking into account certain heat treatment conditions, the hardness of the pillar is more than you can account for the carbon content inferred from the ferrite perlite compositions. So what we believe is that it is in the worked condition, so that's why the hardness is more than what is expected in an annealed ferrite perlite condition. So that is another information what we could obtain. And also if you see the ultrasonic longitudinal velocity which we have measured, because the cross section being small, we are able to use reasonably high frequency, and we obtained good ultrasonic velocity information. So from the ultrasonic velocity information, what we believe is that for the given thickness, we know that standard velocity in steel, the velocity what we are getting is much less. That also accounts for a lot of voids or the material is not continuous. But we did not do the radiography here because already simple ultrasonics itself has given us the required information, and also we had only certain time limit allowed by the Archaeological Survey of India to carry out these studies. So these are some of the studies what we have done on the 2 iron pillars, and since time is short, I try to go through very fast, and thank you very much for your attention.
Thank you, sir.
If you have seen the calcium,
Yeah.
so there is some amount of dephosphorylation perhaps. The phosphorus is lower also.
Yeah, so that also could be the
Deformation bands also you are seeing.
fantastic, sir. That also could be the reason for higher corrosion.
Yeah, so now I request Commander S.K. Mishra to share his thoughts.
We have also done a lot of work on musical pillars. So maybe some other time I can tell you. So you can pull out. And we have done a lot of things on coins, South Indian bronzes.
That's right. That's right. Yeah.
Very good scientific investigation done on musical pillars, giving that these are technical. This is pointer.
Yeah.
Good evening, ladies and gentlemen. I'm from the Indian Navy, so I'll be talking about the metallurgical aspect of shipbuilding. The Indian shipbuilding today is fairly advanced. We are the only country after USA, Russia, China, Britain and France who manufacture their own submarines and own aircraft carriers. So our shipbuilding country is fairly advanced, and we consume thousands and thousands of specialty steels every year. I'll rush through the history of the Indian shipbuilding, before I come to the modern part, Indian shipbuilding industry is as old as the Harappan civilization, that is 5,000 years from now in past. The excavation at Mohenjo-daro and Harappa have proved that they had the trade with Mesopotamia in those days, 5,000 years back. They also had the repair facility for ships, because a dry dock has been discovered in Gujarat at city of Lothal. I'm rushing through it. Please pardon me. This was the route from Indus Valley civilization to Mesopotamia, the trade route. Now, the location of Lothal, you can see, it is on the mouth of a river when the river meets the sea. And the ships used to come here for repairs and for trade. This is an artist's view of the Lothal shipyard, where the ships used to be repaired and berthed. Coming to the Vedic age, the Ramayana Ayodhya Kand has got description of 500 boats loaded with hundreds of soldiers and hundreds of oarsmen to drive it. Even Mahabharata has a reference for sailboats. I'm rushing through it. In case you want me to be slow, please tell me. Coming to the Nanda and Maurya empires, these empires had trades and had a fighting navy. And the Chandragupta and Ashoka had sea trade flourishing, and Ashoka even sent his son and daughter to Sri Lanka for the spread of Buddhism. Can you hear me? Now, after that, the Satavahana Empire had trade with Romans. The trade during Satavahana Empire expanded so much that the Romans were run out of their gold. And this is how the India became the golden bird. See the sea routes right from India to Far East and towards the Rome. Coming to the Gupta dynasty, this was a time where we had our astronomers, Aryabhat and Varamir, and they mastered the art of oceanic navigation by stars, because they accurately mapped the stars' positions. During the Gupta Empire, you can see the expansion of sea trade going right up to China, through Java, Sumatra, Indonesia, Malaysia, and this is how the culture of India went to these places. Then the southern dynasty were no less. The Chola Empire, the Chera Empire, the Pandyas, they had extensive sea trade with Far East. And these were the empires who built those great temples in these places and took the Indian culture to them. Then Shivaji had a fighting navy. And if Shivaji had not had this navy, we would have been subjugated by Portuguese and British 100 years earlier, because these navies fought Portuguese and British for a long time. And Kanhoji Angre was their admiral, and Indian Navy has named one of their ships by the name INS Angre in Bombay, in his memory. Now, another chapter of Indian maritime history was written in 71 war, when in war with Pakistan in Arabian Sea, our missile attack was so furious that Pakistan had to withdraw all their ships in their harbor. No ship was left in the sea, because the ships at sea were sunk by missiles or were damaged beyond repairs. So that was the unanimous victory of India. Yeah, I was part of the ship. I was part of this battle. And I was a young lieutenant of 22 years at that time. That was 1971. Young left, joined Navy only 3 years ago. This is the kind of missile boats that fired the missiles on Pakistan. And even on Karachi harbor they attacked, and Karachi refinery was burning, it was ablaze for 10 days. Ancient art of shipbuilding was the best in the world in India. Even when the British came, they said that the Indians are building ships which even the British cannot build. And they learned a lot of things from Indians. But the Indian shipbuilding industry was killed by British because they made discriminatory laws. They said that any cargo to England will go only by the ship owned by British and not by Indians. They made such discriminatory laws that the shipbuilding industry of India, which was so good, was entirely killed. Now, coming to the modern shipbuilding industry, after independence, the shipbuilding industry has again picked up. And today, as I said, we are the only country after those 5 advanced nations who build our own submarines. This is a submarine built at Majgaon dock. I was at this yard building ships and submarines. The aircraft carrier Vikrant, recently commissioned last year, it is a 45,000-ton vessel and has used 30,000 tons of specialty DMR steel, which has been supplied indigenously by Steel Authority of India. This is an import substitution product. If they had not done the research into this, this would have been imported. 30,000 tons of steel coming from abroad, you can imagine what will happen.
DMRL has made.
So, DMRL, yes, it is called the DMR steel, a special DMR steel. Now, this aircraft carrier is in service today. This is the first aircraft carrier built by the Indian Navy. Here it is. Today, we are building the most advanced ships. None of the ships are coming from abroad. When I joined the Navy, we had all British ships. Then the Russian ships started coming. Today, no ship comes from abroad. All ships are made in India. This is a ship made in Majgaon dock. And the other shipyards, the Goa shipyard, the Visakhapatnam shipyard, the Garden Reach shipyard, they also build warships as well as merchant ships. Today, our shipbuilding industry is fairly advanced. Now, what about the future? What will we need in future? The ships will need to get faster and faster, because faster the ship is, more performance-wise it's better. Because if it's a lone hunter, it needs high speed. If it is hunting submarine, it needs high speed. If it is supporting an aircraft carrier, it needs high speed. So we will need metals that are lighter, because the lighter the ship, more is the speed with same power. And the research needs to be done in lighter material with higher strength. Russians are very good at it. Russian ships are far lighter. They are using metals and alloys which are lighter. Russians have overtaken British in this technology. Also, the sea environment is corrosive, underwater as well as over water. So you need these metals with corrosion resistance. Now, not only the ships, the weapons of the future will also demand better materials. They will demand metals which are high strength as well as stable at high temperatures, because the missiles engines will be stronger. The missiles will have the higher speeds and they will have to bear that high temperature. Now, new metals need to come up. Missile speeds will always go up. If they are doing 10 marks, tomorrow they will do 20 marks, because faster a missile, more difficult it is to shoot it down, because you need a missile faster than that. So whosoever advances in this technology will be the winner. Today you don't have to see the enemy to destroy him. You have to fire a faster missile so that it can kill him before his missile comes and destroys your missile. So here you will need material. This is our BrahMos. This has been installed on the Indian Navy ships. And today we have Arihant submarine, which is a ballistic missile submarine. So the ships and weapons both will demand higher speeds and better metals. Thank you.
Thank you, sir. So I request Dr. Vinod Kumar to share his thought.
Sorry, sir. Hope I have not taken much time.
No, you have not taken, sir.
I had to rush through, but
Actually, so I have prepared for 15 minutes talk, but unfortunately because of time limitation, we have to sort it out. And I was supposed to cover acknowledgement, history of wood steel, trading of wood steel, and characterization of wedge-shaped artifacts, so that we will able to understand why wood steels are somehow more tougher, corrosion resistant, as well as this wear properties was also very high, and what are the future challenges, and then conclusions. So I will only take 1 minute on each slide quickly. So first of all, I would like to acknowledge my supervisors, late Professor R. Bala Subramaniam, under whom I worked during my MTech, and part of this presentation having that work. And another one is, this guy is Matthew Barnett. He is my supervisor. And this is Jack Kishan, who is a from science background. And I would like to acknowledge my lab mates at that time, in 2008. And these are the history, just I am skipping that part. And this slide is very interesting, because here King Richard and Sultan Saladdin both are testing their wood steel by cutting the iron rods and by cutting the pillow. So these are the different quality wood steel having. So these are the some you can say crucibles. I am not going to go into that detail. To understand the trading of wood steel, you will be surprised to know that the Indian Empire and this Bactria, so those having the 2000 years ago, India and Syria were a kind of neighbors. Okay, and there was a good trading between India and this Syria. So Syria here is Damascus, and it is a misnomer. People used to say that Damascus steel. In fact, Damascus sword is there. Steel is our wood steel. Okay, so these are some you can say misconception in the literature. Now this is the sample we have procured from this Kona Samudram, near to Kona Samudram, during the survey of South India. And this Jackson has helped us a lot, and it has been characterized, and we found that chemistry wise this sample is coming in between other Damascus swords, and we have also observed that cerium and this niobium type of alloying elements were present, and these are the microstructure evaluation, and this from low strain region to medium strain region and to very high strain region, and we were able to see the random distribution of ferritic grains, and there was a kind of this banding, carbide banding was also there. And I would like to show the this work published in Nature. It claims that at the edge of the Damascus sword, the carbides are present in form of carbon nanotubes, and that is one of the reason why those steels are being so tough. And we were able to somehow cut even steel rod, as well as we were able to cut that pillow by using this Damascus sword. And now these are the future challenges. We assume that steel is a established research area, but considering the Vision 2047, we should also target that this, in spite of the fact that there is a very less scope of publication in case of high carbon steels, particularly in case of wood steel, but we should focus, and government should somehow provide some initiative, and I am happy that IKS is taking interest into such kind of thing, and they are financing. In our department, there are 3 such projects funded by IKS, and I also, through this forum, I would like to convey that Ministry of Steel should take proper initiative in this direction, so that this archaeometallurgy in India should be addressed properly. So with this, I would like to thank IKS, Ministry of Culture, for organizing such event. And this is the conclusion part, including all those processing up to this final product of Damascus sword. And these are the few references from where I have taken these contents. Thank you.
Yeah, so now I request Professor Ballal to finally conclude.
I don't think I want to say anything. I already said a lot.
Then I think what I suggested that there are some couple of questions what actually our panel need to do. Finally, what should we have the vision for next 25 years? So that white paper we should get out of this. So I request panel members to be please come on the dais, and I request to just have some kind of a discussion regarding whatever the wisdom we have from our ancient. So that the whatever the ancient knowledge we have. So from this, what strategy we should adopt for the future of metallurgy, and how we can excel in this particular field in our country. So I think anyone from you, please start with.
If you permit, then I'll begin with 1 or 2 minutes. Now, I was learning from the past, as far as iron metallurgy is concerned in India, and future. Having spent 12 years, or about 12 years with the steel company, and today I'm using the steel in the automotive. So where do you go actually? Can we use any of our ancient knowledge in these areas? When we are talking of 122 million tons that India produces, or 5 million cars which you produce, can we use some of our old knowledge? If I put myself in that position, I don't think the trajectory is very much visible. It's not very clear. However, there are a few things. One of them is, of course, the Damascus part, or the high carbon material, where a lot of interesting things can happen, from divorce eutectic transformation to divorce eutectic transformation with associated deformation. Those are all academic kind of thing. But if I'm talking of the still in the future, and from 122 million tons, you want to go to much higher level of 330 million tons, two things come to my mind. One is, where are the ores? As Professor Ballal said, the magnetite part is on the western part of India. The eastern part, which is currently the capital of steel making, this is hematitic. So here in this area, the ore itself, or mining itself, is going to be a big challenge. So raw material challenge. So today, people may not know here that when you do the mechanized mining, huge amount of fines are produced. And plus all steel plants, when they wash the ore, then slimes are there. These are super fines. Using those in the steel making has been a challenge. So these are actually steel making challenges. We know what to do with that. Alumina is higher. Interestingly, in Indian bauxite we have iron, and in the Indian iron ore we have alumina. So we have problems. If the alumina goes up, the blast furnace productivity comes down. These are all well known. So therefore, what all the new modern steel plants, including Jindal's and the Nippon Steel, ArcelorMittal, there's a new company, all these, whatever they are doing is collecting all these fines through slurry transportation. So slurry transportation is no more a technology which is in the laboratory. No, we have about more than 600 kilometers of slurry transportations of the fines. So fines we just heard from the lecture. I didn't know from the lecture of Professor Ballal that there are villages or people who are using fine ores and making or trying to make, but they are using unfortunately magnetite, so they have problems in reduction.
They make the best steels of
best steels. So therefore, here is an example. This is the first example I find where from the powders also, that means very fine ores. So fine ore utilization in India was not happening 10 years back. Today it has become a must, number one. Number two, extremely high iron ores, government we have stopped it. So it is not 55% plus, so you have to use 50% and so on. So that's also a bigger challenge. So beneficiation and the instruments, etc. for that. So here we don't have the ancient thing, but we can learn actually from the low carbon and high carbon ancient metallurgical process.
Yeah, so please, Professor Ballal, please share your views.
Yeah. See, technology is very specific to region as well as time, because as against science. So transporting some 2000 years old technology to modern times is foolish. It doesn't work. You know, you can't make wood steel now because there are alloy steels which have tremendous properties. Why would you break your head on making woods? But what is transportable is the knowledge of understanding behind underlying science. Why did use wood steel get the property it does? That is a question worth exploring. Not to reproduce woods. What is important is the science behind our technology over the years, because the knowledge is what is transportable. The understanding part of the knowledge, not the technique, but the technology behind the technique is what is transportable. So we need to do a lot of PhD kind of work rather than MTech kind of work, on trying to understand. This is
one small point, addition to what Professor Ballal has rightly said. For example, superplasticity, which with so much of care and research we are doing, we believe that ultra-high carbon UHC material, which Vinod is using also here, is a superplastic material. As Sarvi said, the Damascus swords revisited the question mark, but that introduces superplasticity. So with the high carbon material, normally we think that this is brittle and strength is high. But no, we can also make it highly ductile, as we will show also. In NML, we recreated that. Thank you. So we learned some lessons.
Yeah. That is what is important. And going into the future, as you say, that it is a knowledge economy that is becoming important. So our emphasis on building up scientific knowledge is very, very important, because that is where the present day is. Present day is that of science. So we can't go back in time.
Right. I think that's not important.
Let's not keep on glorifying our past and stay in the past. That is for old, tired people like me. Young people like this should look forward.
Right.
May I have to make a point?
I just want to make only one point with respect to the phosphorus. All of us know that it is giving cold sharpness and then it should be removed. But can we adjust? Okay, can we adjust the process parameters so that we retain phosphorus and make a more a relatively cheaper melting and consolidation process, but effectively utilizing the process in a more microstructural control manner through the thermomechanical processing. So if we do that, I feel at least we get one benefit of the doing all these studies and realizing that phosphorus has very good role in corrosion resistance. Thank you.
Yeah, I forgot this point. Most of the time, our problem must be modern post-independence technology has been that we import technology from Europe or Japan. As I told, they are location specific, they are culture specific. Like this phosphorus problem. Phosphorus is good in the tropics, but it's not good in cold countries because it increases DBTT. So they have driven see the Howrah Bridge, which is standing so well. What is it, phosphorus? 0.6. Now we say 0.15 is too high. Why? Because when they laid the Siberian oil line, they were breaking because it is minus 20, minus 30 degrees. DBTT crossed, it was cracking because of high phosphorus. So they have drawn it too. So we have to make steel which is for the tropics. We can't get it from alumina. Problem is the same problem. Nobody else has got. If you improve blast furnace technology from Europe.
The only issue there, this is very important. Only issue is Indian steel is not used only in India. In India, we are using actually a lot of imported steels. And our steel also has to go abroad. So therefore, the previous kind of economy in which you are operating was a kind of different kind of economy today. Today, our automotives, our steel and our bearings, it has to go round the globe also. Make in India, but they are meant for the whole world also. So which is why this business of, but how to tackle phosphorus, we know exactly. 3D atom probe we use, and you put niobium or boron so that grain boundaries you fill up, and phosphorus you drive out of grain boundaries. That's a physical metallurgy. Thank you.
I think what the panel members have said. In addition to that, I think a lot of research needs to be done in mixing metals, in alloying metals, to produce new alloys which are lighter and tougher. Also, the bonding of various materials, which will give you lighter materials and tougher materials, and the materials that stand the extreme temperatures.
Commander Mr. I just want to add here, the new steels in the past 20 years, I think Murugan was here. 3 days back, we had a 2-day conference, international conference, only on the global conference. So all of you would like to know that the ultralight steel auto body program, in which 33 steel companies in the world combined, and we were the only one from Tata Steel then. So ALSAP, which is there on the net, you'll find, hyphen AVC, Advanced Vehicle Concept. So therefore, TRIP steel, BH steel, the Queen's Protestant steels, all these are being produced in India. So it's not as if the knowledge is only one side. So practically we know exactly what is the high strength steel. These are called ultra high strength steel. So high strength and toughness, as Professor Ballal also said. Combination of that, which is being used in our automobiles today. So the automobile body has come down. Car weight has come down with ultra light steel auto body program. This is a global kind.
But there is no end to this race. Future will demand still better materials, and the research has to go on to meet the needs of the future. What is there today, tomorrow will need even better.
Right.
Yeah.
Yeah.
So I have already covered my point.
Yeah.
And one thing, based on the discussion, what I think, we should somehow suggest Ministry of Steel to have a kind of PhD. Ministry should support PhD programs so that local technology should be developed, and we should also target few ancient, good quality, you can say, materials, which will be useful for different applications.
And also for the education, like the education system.
Correct.
The awareness of
Yes.
Yeah.
Yes.
Yeah.
We cannot replace steel. This is the fact. So we have to live with steel, and we have to work for that.
No, since you raised the education, I have a strong criticism with respect to all IITs and NITs. Unfortunately, they have moved away from metallurgical engineering to metallurgy and material science. This is very, very unfortunate. Let me put it bluntly. This should not have been allowed by the powers that be or whoever it may be. This is a wrong strategic mistake we have done. I am sorry for that.
No, you are right, sir. You are right. No need to say sorry. It is the real fact. Ji.
Yeah, please.
Yes.
I'll be brief. I have 2 points. One is related to this Agaria technique. In fact, that is part of my presentation or panel discussion tomorrow. What I have in my mind is that the ladies or even the gents, family-wise, they are working on it. Whether the fines which are available at mine site, which he had just now said, whether they can be used by them and make pellets out of it and use a kind of portable small furnace which they can produce small quantities of steel. There is a buyer for it who, like a mini steel plant, where they take these ingots and then pay them some price, so that this steel is used in their bigger furnaces. Okay, so this helps in Ministry of Culture and Social Welfare. Also, it helps them that you don't relocate the agarias, because many of their families might have left the profession and might be going for software industries. I mean, I'm just quote in unquote. But if you want to retain their cultural heritage and also economically you want to bring them up, this is one solution which I have. So maybe that can be considered by...
We have started doing that, for some of the brasses, bronzes in Odisha. And the pellets which are produced today, all blast furnaces we use, of course, we are using pellets, we are using sinter and sidezone. But he is telling the pellets could also be made available to the
Yes,
Adivasi, so that
Adivasi.
it becomes easier for them to process. So you can sustain it. It's an interesting possibility.
Yeah. Dr. Ballal.
Now we have to finish. One more point, sir.
I just respond.
Yeah.
My colleague, Dr. Buddhe at Gandhi Institute at Benares, he was working on that. That's how I could go. Otherwise it's very difficult to get into a tribal area. I had a nice anecdote, but this is not the time. So he called an Agaria Panchayat. Some very last area, some 3,000-4,000 Agaria came. They had a 3-4 day Panchayat to discuss about their problem. When they were asked, what is their priority government intervention? They said first is education for them. Their children should get out of this profession. Second is agriculture. Then they said third one is, yes, we want to maintain it because it's a religion for us. See, that Lohasur is whom they worship. So they continued their furnace working for some time basically because Lohasur comes to their house. Otherwise, they are no interest. It's a back-breaking work with very low rate. And it's based on charcoal and not on coal. And the charcoal, they are not allowed. See, we could only find Agaria existing in places where the truck would not go. When the truck goes, all these things go to the timber lobby and not to Agaria. Agaria will not be allowed to come.
So,
Yeah, that kind of...
here, connected with this, actually, is you can think of this. If you go to the net today and find out ancient iron making, how many YouTube things are there. I was teaching it also both in Kharagpur as well as in Bhubaneswar. You find at least 5 to 6 YouTube fantastic kind of processes. They have rebuilt in Burkina Faso, for example. So Burkina Faso thing you will find, and you will find also in Western Africa, Eastern Africa also, YouTubes. How many YouTubes are there? We should have given actually a lot of facility to Professor Ballal. So excellent YouTubes on Agadia iron making, even in NML. I feel very sad now. And we did not make those YouTubes those days. But today it is necessary to preserve the technology so that it is in animated form.
Yeah.
I think in MP that Museum of Man or something.
Yes.
Yeah, Professor Bhanuprakash, late Professor Bhanuprakash from our institute had gone to Agarias and he also made, and there are some video recordings that he made and he has submitted to IAM, if I remember correctly.
Internationally, today, if somebody in the US wants to know how the Indian ancient iron making process is, he will get a lot of information from Europeans and from Africans. And the African thing is made by the Europeans, but we don't have many.
Yeah, no, but what we are discussing here is how to carry it forward, if we can carry it forward, the old technology. Yeah, my second point is already mentioned by Dr. Jaikumar, that is, why not reverse this process to some extent? Instead of removing phosphorus and re-entering, can't we learn from that and directly produce without removing phosphorus? I mean, steel experts are here.
All electrical steels, we have a lot of phosphorus, deliberately because of punchability and because of magnetic aging resistance. So those are instances where high phosphorus is there.
No, that is because Westerns are using.
We have to go in our own.
Can we get into high phosphorus
So
reinforcement?
So reinforcement, we have done the TMT device for buildings. We have now a grade where phosphorus is high but not at the green boundaries. But if you don't ensure that, then there will be disaster. This is what I am trying to say.
It's really wonderful discussion today. So I think all panel members has contributed enormously to give the vision white paper on this for the next 25 years. So definitely we will work on this. So now at the end, just for the students who are sincerely attended this event, so I just one question I want to ask because we want to give them reward if they answer it properly. So which